right, this video is for those of you that were not in class covering section 4.6. Hopefully y'all get to feeling better soon, but I want to go ahead and go through the notes. When I email this, I will hopefully remember to email a copy of the PowerPoint as well, or I've got it here in the class. Okay, so let's go ahead and start. Section 4.6 gives us a little bit more variance, a sort of a version of the congruency postulates and theorems that we've covered so far in chapter 4. These are specifically related to right triangles. And there's a separate video that I just posted that covers an additional proof that I'll talk about here in a minute. But let's go ahead and start off. So first off, we have the parts of a right triangle. The side opposite the right angle is called the, let's see what color this is. Yep, I'll put it here. Hypotenuse. Hypotenuse. Uh-oh. I'm having some technical difficulties. And then the other two sides are the legs. Both of those are called the legs. So this is the hypotenuse. That in white like I meant to. So we will use these. We have the leg, hypotenuse angle, and the leg angle congruence theorems that are special cases of our more general congruence theorems or postulates like side, angle, side, 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 angle, angle, side, etc. Okay, so we'll show the connection between those two as well. The first one that we have is the leg theorem. So if the two legs of one right triangle are congruent to the two legs of another triangle, then the two triangles are congruent. So let's look at the example that we have down here. So if we label these side, we know that all right angles are congruent because they're exactly 90 degrees. So we have side, angle, side. So this matches with the side, angle, side congruence postulate that we already know. So that's because of the right angle, essentially just the reason it only has two, it's LL instead of side angle side, is because those right angles are understood to be congruent. They're all 90 degrees. So it eliminates having to prove that third part, corresponding part of the two triangles. Let's go ahead and look at this in a proof. And this proof essentially works for the others that we're going to talk about as well. So in this case, let's see, y'all have extra room on your slides. I really don't. Let's see if I can zoom in here. It should work. I forgot to put this on there. So just add this to yours. The given in this case is our diagram here. So triangle, if we're told that triangle ABC and triangle DEF are right triangles, and they've told us that AC is congruent. Here it goes. Is congruent to DF, and BC is congruent to EF. Then they've asked us to prove that triangle ABC is congruent to triangle DEF. All right, so let me go ahead and zoom out here. So first, we always start off with our given. So first off, ABC and triangle DEF are right triangles. AC is congruent to DF. BC is congruent to EF. All right, so they've only given us two sides, and unlike angles, two sides do not prove that two sides congruent or does not prove that the third side is congruent, so we can't use that. So we simply use the fact that C and F are right angles in order to state congruence. But first, we have to make sure we state what angles are right angles. Then we can state the congruence of those based on that definition. So they've told us that our two triangles are right triangles. So what we have to do is, okay, if they're both right triangles, that means they both contain a right angle. What is it? Well, I know angle C and angle F are labeled as right angles. So I use the definition of right triangles to state this. A right triangle must have a right angle and two additional acute angles. All right, so now that I've stated their right angles, that means that they have to be congruent because right angles only equal exactly 90 degrees. So angle C is congruent to angle F because of the definition of right angles. So therefore, these are congruent. Whoops. And now we know the postulate that proves that these are congruent. We can state that ABC is congruent to triangle DEF because of side angle, side congruence. And that works essentially to prove that leg-leg congruency in right triangles will prove that the two triangles are congruent. Let's look at the rest of these. The second one is HA, which you can imagine stands for hypotenuse and an acute. We talked about this in class as well. It's very important to notice because you'll see this in the definitions that if you have a right angle, the other two angles have to be acute angles because their sum will only equal 90 degrees. So even if it's 89 and 1, they're still going to be acute angles. And we use that to define any angle in a right triangle that is not the right angle. All right, so if the hypotenuse and an acute angle of one right triangle are congruent to the hypotenuse and the corresponding acute angle of another right triangle, then the two triangles are congruent. And you can see this. What does it match? Well, it's angle, angle, side. So this is a version of the angle, angle, side theorem that we already know is true. Just works with right angles. The leg angle theorem is very similar. If a leg and an acute angle of one right triangle are congruent with the corresponding leg and acute angle of another right triangle, then the two triangles are congruent. So you can see with this one, we have angle, side, angle, which is also a valid postulate to prove triangle congruency. All right, so let's look at this. You've got a little table of these. So leg, as we've already discussed, is a side, angle, side congruency. So I'm going to write that. It's just a variation of the side, angle, side. The hypotenuse angle is side, angle, angle. So that one is a version of the angle, angle, side theorem. And then leg angle can be one of both. If you have the two angles and then they have their adjacent side, then we have an example of angle, side, angle congruency. However, if it's the non-adjacent acute angle, you end up with angle, side. Oh, sorry, I did that wrong. Angle, angle, side, because it's opposite that leg. But we'll still be able to prove congruency. So this one is angle, angle, side theorem. Let's see. Let's look at an example. Okay, example one. Sorry, it's a little bit hard to see on mine. I think your slides are probably easier because they're in grayscale. Example one, prove that a segment from the vertex of an isosceles triangle to the midpoint of its base, divides the triangle into two congruent right triangles. So what's our given here? We are given that the, first off, that it's an isosceles triangle. So triangle A, B, C. So given that triangle ABC is isosceles, and make sure you, with isosceles triangles, make sure that you define your legs. Isosceles triangle with AB congruent to CB, and they told us, let's see, the vertex from the segment from the vertex to the midpoint of the base. So they're telling you that M is the midpoint of, I'm out of room, base AC. Then we need to prove that triangle ABM and triangle CBM are congruent right triangles. Okay, should be pretty easy enough. Let's go ahead and start off with stating our given. We know that AB is congruent to CB. And M is the midpoint. AC. Second, we can, so I'm going to start with the whole midpoint part. First off, I know that if M is the midpoint of AC, that means that AM is congruent to, I put two tick marks here. AM is congruent to CM because midpoint, the definition of a midpoint is that it happens right in the middle of a line segment. So that'll give me a side. AM is congruent to CM because of the definition of midpoint. Let's see. So I have a side. They gave me the side for the isosceles triangle. Also, I'm going to go ahead and use side congruency because I love the reflexive property. To me, that's obvious. Line segment BM is a part of both of these triangles. So I'm going to go ahead and say that BM is congruent to BM because of the reflexive property of congruent segments. That line segment is reflexive to itself. So now I can go ahead and, so now I have stated the two triangles congruency. So that's the first part. ABM, so triangle ABM is congruent to triangle CBM because of side congruency. All right, so that's the first part that we needed to prove. So now we need to prove that they're both right triangles. So obviously the important part of this is the right angle. So if these are right triangles, then this would be the angles 1 and 2 that I would want to look at to prove that they're right angles. So first off, we need to talk, so we're going in the opposite direction. Instead of using right angles to prove that they're congruent, we're going to prove that they're congruent and then use that to prove that they are right angles. So first off, I know they're congruent. Angle 1 is congruent to angle 2 because corresponding parts of congruent triangles are always congruent. Now that I've stated they both have the same measurement, I know that they make up a linear pair. So I know that angle 1 and angle 2 are supplementary. I lose my voice here. I know they're supplementary because the linear pair theorem tells me that. Pulling from way back in chapter 2. Linear pair tells me that they're supplementary because they're a linear pair. That tells me that angle 1 and angle 2 are right angles because congruent supplementary angles are right angles. Their sum has to equal 180 and they're congruent. So they have to have the same measurement. So 180 divided by 2 is 90. So now that we've taken the fact that they're congruent, stated they're supplementary because they're a linear pair, then stated that combine those two congruent supplementary angles have to be right angles, we can now state that triangle ABM and triangle CBM are right triangles because they both contain right angles. So that's the definition of a right triangle. Okay, that is all. Let's go ahead and move on. This last one that I want to talk about, again, I proved why this works with right triangles in a previous video. So any of y'all that are going to want to take the SAT or going to take geometry in college, then you're going to want to go ahead and take a look at that just so you have the information behind why this works. But let's talk about the last right triangle theorem. It is called the hypotenuse leg congruence theorem. If the hypotenuse and a leg, either leg of one right triangle are congruent, then to the corresponding, or the hypotenuse and the corresponding leg of another right triangle, then the two triangles are congruent. Okay, here's where it gets a little bit tricky. Now, if we try to connect this to one of the general postulates and theorem that we know about triangle congruency, we would label side, side, angle, and we would see that we have a problem because we know that side, side, angle is a bad word spelled backwards, and we can't have bad words, right? Also, it doesn't work. That does not work to prove triangles congruent. However, it does work with right triangles. And it has everything to do with the fact that one of those angles is exactly 90 degrees and we know it. So there's a different video that goes over that. What I want you to know is that there is no, you would say there is no general postulate or theorem about triangle congruency that will pair up with the hypotenuse leg congruence theorem. However, trust that it works. Obviously, go watch the video if you don't trust me and you want to know why, but it does work when you have a right triangle. Hypotenuse leg congruence theorem will prove two triangles congruent. That is it. There is a homework assignment number 1 through 14. I didn't give you any proofs for homework, so you're welcome. We might look at a little bit of that in class tomorrow. But we're going to review sections 4.5, 4.6 tomorrow, and then we're going to have the quiz on these Thursday. All right, thanks so much. And as always, come to me with any questions or concerns if there's anything in this video that still does not make sense. Thanks, guys. Have a good night.